Hello everyone. On this video, I will be discussing the arithmetic rules associated with powers and roots. Many of these rules are straightforward, but some can be challenging. A lot of us, myself included, had difficulty in school working with powers and roots. I'm going to try to make things a bit easier. Here are some videos you might be interested in. Video number 8, Powers and Roots, will give you a good introduction into the terminology, symbols, and basic concepts associated with powers and roots. Video number 6, Arithmetic Rules, provides some background to the concept of arithmetic rules and discusses some of the most important arithmetic rules. The rules we discussed today are not mentioned in that video. We will be discussing various number types in this video, such as counting numbers, integers, irrational numbers, and real numbers. If you're rusty on this topic, then I recommend viewing video number 2, Number Types. Some quick terminology before I begin. Powers are often called exponents. The terms are interchangeable. Roots are often called radicals. Those two terms are also interchangeable. Rules are often referred to as laws or properties. Don't be confused when you hear people using different terminology. I will be covering 6 rules associated with powers or exponents. They are the product of powers, the quotient of powers, the power of powers, negative exponents, the zero power, and the distributive property of powers. I will also be discussing the relationship between powers and roots, which will allow you to apply all the rules which we have for powers to roots. Before I go into these rules, however, I want to give you a little more information on exponents and radicals. In video number 8, I covered the concept of a perfect square. That is, if I take the counting numbers and square them, then I get the following set of numbers: 1, 4, 9, 16, 25, 36, etc. This set of numbers are the perfect squares. Since there are an infinite number of counting numbers, there are an infinite number of perfect squares. I'm just writing down the first several. I can expand this concept of perfect squares to include all integers. 0 squared is 0. Let's write that down. Now let's take a look at the negative integers. Notice that when I start squaring the negative integers, I end up with the same set of perfect squares as I have with the counting numbers. This is reasonable, since when you multiply two numbers that have the same sign, then the answer is always positive. There are 3 things I would like to point out. The first is that the square roots of these perfect squares have 2 solutions, a positive one and a negative one. In fact, this is true not just for integers, but for the square roots of any positive real numbers. When we deal with square roots in math problems, we usually need to consider both solutions. We often annotate the 2 solutions as follows. In this case, it means that the square roots of 4 are positive 2 and negative 2. The second point is that we do not have square roots of negative numbers. They don't exist in the real world. There is a branch of mathematics called imaginary numbers, which deals with square roots of negative numbers. But our study of mathematics only encompasses real numbers. So, as far as we are concerned, the square root of a negative number is considered to be undefined in the same manner in which division by 0 is undefined. The third point I want to make is one that is not obvious but is important. If we take the square root of a counting number which is not a perfect square, then that number is an irrational number. Remember that an irrational number cannot be expressed as a fraction and does not terminate or repeat when expressed as a decimal. So the square root of 2, the square root of 3, the square root of 5, the square root of 6, etc. are all irrational numbers, both positive and negative. In video number 8, I also brought up the concept of a perfect cube. If we cube each counting number, we get the set of perfect cubes. Again, there are an infinite number of them, but here are the first several. As with perfect squares, we can look at the perfect cubes of integers. Let's do it. I add 0 cubed, which is 0. This time, though, when I cube the negative integers, I get negative numbers. These negative numbers are also perfect cubes. Cube roots do not have 2 possible solutions. They only have 1. Also, the cube root of a negative number is defined, that is, it exists in the realm of real numbers. For instance, the cube root of negative 27 is negative 3. However, cube roots are similar to square roots in that the cube root of any integer, which is not a perfect cube, is an irrational number. Therefore, the cube root of 2, 3, 4, 5, 6, 7, 9, 10, etc. are all irrational numbers. With the exception of pi, nearly all of the irrational numbers we commonly deal with are square roots and cube roots of numbers. Okay, let's go back to the 6 rules for powers or exponents. The product of powers says that when I multiply 2 powers together that have the same base, then I can simply add the exponents. The rule is commonly written like this. The x's in this expression indicate that both bases must be the same number. The a and b indicate that the exponents do not have to be the same number, although they certainly can be. So, for example, 2 to the 5th power times 2 to the 3rd power would be equal to 2 to the 8th power, since 5 plus 3 equals 8. Similarly, 3 squared times 3 cubed would equal 3 to the 5th power, since 2 plus 3 equals 5. As a note, when I start to use x as a variable, I change my notation for multiplication to a dot in order to avoid confusion. We are gradually transitioning to algebra, where the use of x as a variable will become quite common, and using x as indicating multiplication will no longer be used. The product of powers is relatively easy to grasp, since it really is just an expansion of the definition of an exponent. In the latter example, 3 squared means 3 times 3, and 3 cubed means 3 times 3 times 3. 3 multiplied by itself 5 times is simply 3 to the 5th power. The quotient of powers says that when I divide 2 powers that have the same base, then I can simply subtract the exponents. The rule is commonly written in one of 2 ways. For example, 4 to the 5th power divided by 4 cubed equals 4 squared, since 5 minus 3 equals 2. The quotient of powers is fairly easy to visualize as well. 4 to the 5th is 4 times 4 times 4 times 4 times 4. Similarly, 4 cubed is 4 times 4 times 4. I can factor out a 4 in the numerator for every 4 in the denominator. What remains is a numerator of 4 times 4, which is 4 squared. The power of powers rule says that when I take a power and raise it to another power, then I can simply multiply the exponents together. Here is how the rule is expressed. So, for example, 5 squared, quantity cubed, is equal to 5 to the 6th power, since 2 times 3 equals 6. Again, this rule is derived from the definition of exponents. When I cubed 5 squared, it is equivalent to writing it as 5 squared times 5 squared times 5 squared. 5 squared is simply 5 times 5. I end up with 5 multiplied by itself 6 times. That is 5 to the 6th power. Can I have a negative exponent? The answer is yes, but at first glance the expression seems to make no sense. I had difficulty with the concept of a negative exponent when I first studied it in school. The negative exponent rule makes things a bit easier. The rule states that a number with a negative exponent is equivalent to that positive exponent expressed as the denominator of a fraction with 1 as the numerator. The rule is commonly written as follows. So 2 to the negative 3 power is equal to 1 over 2 cubed, which is in turn equal to 1 over 8. The easiest way for me to envision this is to consider a problem like 2 squared divided by 2 to the 5th power. Per the quotient of powers rule, I subtract the exponents. 2 minus 5 gives me negative 3. If I express 2 squared divided by 2 to the 5th power as 2 times 2 divided by 2 times 2 times 2 times 2 times 2, then I can cancel common factors in the numerator and denominator. I end up with 1 over 2 cubed. Can I have a number to the 0 power? Again, the answer is yes, But again, at first glance, the expression seems to make no sense. The zero power rule says that any number to the zero power is equal to 1. Here is how it is written. Again, I think this is best understood using the quotient of powers rule. Let's take 2 cubed divided by 2 cubed. Using the quotient of powers rule, when I subtract the exponents, I get 2 to the 0 power. But we know that any number divided by itself is simply 1. So 2 to the 3rd power divided by 2 to the 3rd power also equals 1. Therefore, 2 to the 0 power equals 1. As a note, the special case of 0 to the 0 power creates some problems for mathematicians. There is no universal agreement within the math community as to the value of 0 to the 0 power. Some mathematicians believe it equals 1, some believe it equals 0, and some believe it is undefined. As far as I'm concerned, it is a purely academic debate. I have never seen 0 to the 0 power occur in any practical application of mathematics. The last rule for exponents that I'm going to cover is the distributive property of powers. This is the only rule which addresses bases which are not the same. Here is the distributive property of powers. If I have a product of two exponents, represented here as x to the a power times y to the b power, and I raise that product to a power c, then I can distribute that c to each of the exponents individually. That is, the expression is equivalent to x to the a times c power times y to the b times c power. Let's try an example. 5 squared times 3 cubed, quantity squared, is equal to 5 to the 2 times 2 power times 3 to the 3 times 2 power. Let's take a moment to work this out. On the left side of the equation, 5 squared is 25, 3 cubed is 27. 25 times 27 is 675. 675 squared is 455,625. On the right side of the equation, 2 times 2 is 4, so we have 5 to the 4th power. 3 times 2 is 6, so we have 3 to the 6th power. 5 to the 4th power is 625. 3 to the 6th power is 729. 625 times 729 is 455,625. We get the same number on both sides of the equation. The distributive property of powers holds true for this example. We can learn separate rules for roots, but it's a lot more useful to be able to correlate roots to powers so that I can then use all of the rules for powers that we have covered. Let's do this. Roots and powers are related as follows. The nth root of a number x is equivalent to that number x to the 1 over nth power. This relationship allows me to express roots as fractional exponents. For instance, the cube root of 8 can be written as 8 to the 1/3 power. The fourth root of 16 can be written as 16 to the 1/4 power. Recall that when we write the square root of a number, we don't bother to write the number 2 as the index. It is simply assumed to exist. I tell my students that it is an invisible 2. But let me remove the cloak of invisibility for just a moment and write the square root of 9 as 9 to the 1/2 power. At first glance, the use of fractional exponents to represent radicals doesn't seem very intuitive, but when you think about it for a while, it begins to make sense. If I took the cube root of a number and cubed it, then I would get that original number back, right? For instance, the cube root of 125 is 5. 5 cubed is 125. This is exactly what I get if I write the cube root of 125 as 125 to the 1/3 power. For the power of powers, when I take 125 to the 1/3 power raised to the 3rd power, I simply multiply the exponents. 1/3 times 3 is 1. 125 to the 1st power is 125. As I said before, the ability to express radicals as fractional powers allows us to expand the use of the 6 rules for powers and apply them to radicals. For instance, the square root of 2 divided by the cube root of 2 can be written as 2 to the 1/2 power divided by 2 to the 1/3 power. Using the quotient of powers rule, I can subtract the exponents. 1/2 minus 1/3 is 1/6. The solution then is 2 to the 1/6 power, which can also be expressed as the 6th root of 2. Here are the rules again, as they are written mathematically, as well as the relationship between roots and powers. Don't worry if you feel a little overwhelmed right now. This is, perhaps, new and unfamiliar to you, but not necessarily difficult. Like so many things that are new to us, it takes practice to learn and be comfortable using these rules. Powers are used most notably in something called scientific notation. Scientific notation allows us to both express and perform operations on very large and very small numbers much more easily. In the next video, I discuss scientific notation. This will be our last arithmetic topic. In the meantime, have a great day, everyone.
We hope to see you at Veterans Upward Bound very soon, and recommend a friend.